All right, let's go ahead and get started today with lecture 5 on Z-transform. I think last time I was desperately trying to feed it all in and get it all done right before we ran out of time to sort of summarize all the possibilities for the region of convergence. So we'll start off today by trying to recreate that summary. So properties of the region of convergence. And for the purposes of going through these properties, we're going to assume right now that x of z is a rational function. So p of z divided by q of z. Some polynomial in the numerator, some polynomial in the denominator. So a rational expression of z. Given that not every region of convergence is possible. So the rock has 3 forms. So we denominate them A, B, and C. A. Well, you could have a region of convergence like this. Small r, capital R, for meaning it's going to be right-sided. And so Z is, the region of convergence is all Z greater than this constant r sub r, which means you're going to be everything outside a circle, and you're going to be a right-sided sequence. Of course, the other alternative is you could have all Z less than some constant r sub L, less than infinity. So now everything inside a circle, that's going to be your left-sided sequence. And then, of course, there's also the donut option, right? You could have Z we'll put infinity on there, of a form like this. So it's everything less than some constant, greater than another. So it forms that annulus that we were talking about. So for our second property, we talked a lot last time about the Fourier transform, whether it existed, and how that related to the region of convergence. So remember that x e j omega exists if the rock included the unit circle, because that meant it was absolutely summable in that position, and so everything's fine. So we'll say exists, and I think we can use this technical term, if and only if. The region of convergence includes unit circle. So every time we saw the region of convergence include the magnitude of z equals 1, we knew the Fourier transform existed. Another one that almost seems too obvious to write down is the rock cannot contain any poles. So if you're doing a pole zero plot, you don't want to put a pole somewhere and do that. That's obviously something went awry there. You can't do that. Region of convergence cannot contain any poles. So no poles. It's either outside the pole or inside the pole. And I think I drew it here. Oh, zeros. Zeros. So I think it can include zeros. You just can't include poles because it goes away, I think. I'm trying to think if there's any edge cases to that where, yeah, I think it can include zeros. Yes?
There is one example where a pole was on the edge of the region of convergence, but it was canceled out by the zero. So is that the case when a pole can technically exist? It just has to be canceled by a zero.
Well, if it's canceled, then it doesn't really exist. But, right, there might be some edge cases out there. That's a good question. Is there any way it can... I think it could contain zeros. There's no prohibition against it. That's good, though. So property 3 cannot contain any poles. The fourth property, and so this is the easy one that we went through, where if x of n is a finite duration sequence, there's not a lot that can go wrong when it's a finite duration sequence. There's only so many terms. So if x of n is finite duration, and that was the sequence of the form of like a to the n, z to the minus n, the sum as, you know, n goes from 0 to capital N minus 1, one of those type of things where there's only, you know, capital N number of terms. So if it's a finite duration sequence, the rock is entire z-plane. So it can be the entire z-plane with two exceptions. Except at z equals infinity or z equals 0. I think you can think of a good example, you know, if you had a term like that somewhere in the expression for x of z, then you have a, if you put z equals 0 in here, this thing blows up, so you can't have it there. One of the things we talked a lot about was if sequences are right-sided or left-sided, which may seem like a pointless technical detail at the moment, but we're going to get to why it has some why it matters here in a minute. So if x of n is right-sided, then the ROC, region of convergence, is of the form z greater than p max, where this capital P max just means the largest magnitude pole. P for pole and max for the maximum. So it's back to that shape. That means you're right-sided. Of course, if we have right-sided sequences, if x of n is left-sided, then we have the other occurrence, right? Magnitude of z must be less than p min, where this capital P means pole and min is the minimum value. And finally, we've done right, we've done left. The only thing left is two-sided, right? So if x of n is two-sided, what do we have? The rock is a ring, or an annulus, if you want to think of it that way, or a donut bounded by poles. So that sums up, well, I guess there's one last one. The rock is a connected region. And by connected, it means contiguous, things are touching. You can't have weird regions of convergence. And here's a for instance. Suppose I had an annulus like this. Well, that looks fine so far. Maybe there's poles. And then I had another annulus, like this, with more poles. You can't do that. You can't draw bullseyes. That's not allowed. So everything has to be connected. Is that kind of clear? You can have connected regions, like everything outside a circle, everything inside a circle, or a donut, but you can't have two donuts. You can't have things that aren't touching. Now it turns out with all these rules of the road, we can kind of narrow down what happens. So given the poles and given these rules, you can kind of immediately know what the region of convergence is or the possibilities. And so then you know what the sequence is going to be. So just as an exercise, we'll do an example so we can kind of apply the rules and you can see what's going on. So let's do a pole zero plot with 3. It has 3 poles. So what we're going to do is kind of go through what are the possibilities and what are the implications. So given this, I just want to put a find on here so you can remember what we're doing. All possible rocks. So let's start out with our given here. There's the unit circle. And we'll have 2 poles inside, A and B, and 1 pole outside, C. So given this, what can we do with it? So I'm going to kind of hold this off to the side as our given. And now we're going to apply the rules and see what's happening. Well, I'll start with the right-sided sequence. That's kind of the most comfortable way to start. So if our rule is, I think we have, if xn is right-sided, then the rock is magnitude of z greater than p max, or p is the maximum pole. That would be C in our case. So one possibility, A, B, C, and this is where it might get a little confusing. Let's see if I can put it all on screen. A pole at A, a pole at B, the unit circle, just so we can see it. It's not a pole, it's not a 0, it's just there. And then a pole at C, and our region of convergence is Z, all Z greater than C. And maybe we'll do that since it's the largest magnitude pole, just to remember the rule. So if we were shading this, we'd say, okay, that's everything outside of C. So what does this tell us about the sequence? Well, first of all, we know that it's right-sided, and it does not contain the unit circle. So that tells us right now Fourier transform does not converge absolutely. So we'll say Fourier transform does not exist.
So if the P max is greater than 1, then it's right-sided?
Oh no, because we're going to go through all possible choices. There are other choices. We're just kind of exploring the choices of what it could be. And I think I'll put it on a different page so we can kind of keep track of these. So obviously we did the right-sided. What if we made the whole thing left-sided? That's the obvious next step. So let's do that. We have A, B, C, unit circle, magnitude of Z less than A. It goes back to our rule. This is a left-sided sequence. And also it does not contain the unit circle. So we also know for this particular case, FT Fourier transform does not exist. So those are two choices there. Now it gets us to the annulus cases. It can be greater than one pole and smaller than another. And since we have 3, we're going to have 2 cases like that to look at. So let me see if I can move this up. And redraw this. A, B, and C. So another possibility is that it's all Z greater than A less than B. and we'll put magnitudes on everything. So we're in there. And since, as I said, the unit circle is in that position, we also know that Fourier transform does not exist, but first, is it right or left-sided? We know it's two-sided because it's that annular region, so the sequence is two-sided. And we also know that the Fourier transform does not converge absolutely, so Fourier transform does not exist in this case. I'm just trying to cycle through applying the rules to all these possibilities. That doesn't necessarily mean that, in normal problems, it's going to be limited because you start with one and you do some processing. You're going to apply an impulse response, or you're going to apply an impulse response to a signal. What's the output? What's the unit? What's the region of convergence? So you can do the inverse Z transform. That's where we're going with all this. So you can kind of know that not any sequence will result. You have to keep track of the rules.
Question.
Yes.
So in property says if it's two-sided, ROC is a ring bounded by poles. So can a ring be bounded by pole B and pole C?
Yes, it can. That's our next example.
Oh.
Yep. Very good. Stole my thunder. That's right. That's exactly where we were headed.
So
Nope, that's good. You're keeping up here. And let's see, we're way off screen here, so let's try to get back. And as was just mentioned, what if you could be bound by these, B and C? So we get the larger donut. So Z will be greater than B but less than C. So again, this is two-sided. Two-sided sequence. Sorry, two-sided sequences. Two-sided sequence. And one thing that's hard about doing this lecture is it seems like it's been forever since we covered the Z transform formula, and so it almost seems like, where does this stuff come from? Right? It's like, it's sort of arbitrary and capricious rules. I'm just, if it's this poles, then it's that. Well, sadly, we'd have to go back to the original Z transform expression to see how these come out, and we kind of did that, but it's been a week. So if it seems a little mysterious, go back and revisit the prior lecture, because that's where we dug down into the Z transform expression and saw, oh, this is where it will be a left-sided, this will be where it will be right-sided. So we've got this, but what does that tell us about the Fourier transform? Well, region of convergence covers this unit circle, so Fourier transform exists in this case. So that would bring us now to, that's all the possible ones. Now, you could obviously make a mistake and think A and do this and say Z less than A, and then Z between B and C, and you'd be wrong. Can't do this. Not acceptable. Why? It breaks Rule 8, where the region of convergence must be contiguous. So, no bullseyes or things like that in the region of convergence. So, this is not possible for rational functions of Z. Now, we're not going to go into non-rational ones. I'm not sure those are very useful, but if there's any mathematicians in the audience, you might find that there may be, in fact, weird cases where it has weird shape, but not for us doing more normal type processing. So, okay, let's move on to the next topic, which is, okay, now that we have these on our sleeve, up our sleeve here, let's do something with them. So up to this point, we've been discussing poles and zeros as some general sequence. I didn't say it was an input, I didn't say it was an impulse response, I didn't say anything about it. We said general sequence, we're going to play with it. Well, now we're going to say, suppose you know it's an impulse response. What does that tell you about the system that you're trying to analyze? So now we're going to kind of revisit that and say, if the sequence is an impulse response, what does that tell you about the system? And it's going to tell you about whether it's causal or not. It's going to tell you whether it has a frequency response. It's going to tell you things of that nature. So let's start that discussion. So H of n, impulse response, that's what we've been using that H of n for. And we'll say now that we can do a Z transform pair notation. So H of n, Z transform is capital H of Z, which is also called the system function. So that's our terminology for this discussion. Now, if you remember our criteria for a stable system, what was that? That was if you could sum up H of n, if it was absolutely summable. I guess we'll put all these on here. So if the impulse response is absolutely summable, the system it describes is stable. So that was a condition for stability of the system. And we could also say that HE of j omega exists, which is pretty useful because that is the frequency response. And I hope in homework 1 we kind of pounded all those concepts home about how to use frequency responses and the importance of the complex exponentials. If you can tear anything into complex exponentials, you can use the frequency response to easily construct the output. And I guess if that's the case, what else can we say? If you know this, then the rock of H of Z contains unit circle. Right, and it kind of goes back to if H of n was a general sequence and its rock contained the unit circle, then you'd know the Fourier transform would exist, which we like to call the frequency response when we're talking about impulse responses. So now with that terminology, let's go through and say, okay, given we have some H of n and we have its poles and zeros, what does that tell us about the system? So as an example, we'll be given H of Z pole zero plot. So we'll start there. And what we're going to do is kind of like that first example, is find the choices for the rock, which basically means just applying the rules and seeing what sticks in some way and is not inconsistent with our principles there. And then we're going to take it one step further and say, find the choices for the rock and I guess the implications for the system. So I think of a succinct way of writing that. Choices for the rock and I guess implications. Or what features are going to pop out of this system based on these choices, because it will change things. So let's go through and see what it does. So as start, we'll have a 0 at 0, a pole at 1/2, another pole at -2. And there's the unit circle. So we're starting here and we're going to go through our choices. So there's our starting point. Now just like what we had before, we could do right-sided or left-sided. I'm going to start with left-sided. So I'm putting choice number 1 because we're choosing these and watching what happens. if z is less than 1/2, magnitude of z less than 1/2. So there's our 1/2. There's our badly drawn circle. And there's the region of convergence. Still got a pole hanging out here at -2. We've still got unit circle right there. So what does this tell us about the system, if this is h of n? Well, first of all, since it's that form, h of n is left-sided. Which almost seems like no new information, except what does that mean if the impulse response has values less than 0? That has an important implication. It means the system is non-causal. That goes back to, I guess, to our whirlwind recap of linear system theory that we did in lecture 1. So system is non-causal because h of n does not equal 0 for n less than 0. So once we know 1, we can say 2. It's left-sided, non-causal. See if I can get all this on the screen. Also, it doesn't cover this, so where can I put a 3? Fourier transform, we'll just say does not exist. So if the Fourier transform doesn't exist, what else is bad? System is unstable. Because h of n is not absolutely summable. So remember, we kind of went back and forth between if the system's absolutely summable, the Fourier transform exists, and it includes the rock includes the unit circle. So since we don't have that, system's unstable, Fourier transform doesn't exist, clearly frequency response doesn't exist, not a particularly useful system. So, given that, let's choose something else and see what happens. Choice 2. What else do we have? We could do the annulus thing and put z between the poles, or make the rock between the poles. If we do that, we have what? Pole at -2, pole at 1/2. So we have this circle, that circle, unit circle, and coloring it all in makes it kind of messy, but that's the region of convergence. So what are the implications? Well, first off, every time we see the donut, it's a two-sided sequence. That's pretty easy, but if it's two-sided, then it's obviously going to be non-causal because h of n has content for n less than 0. Non-causal. And I'm just sort of abbreviating the explanation here, but the explanation of why it's non-causal is exactly the same as on this page. This system was left-sided, h of n did not equal 0 for n less than 0, so it's non-causal. Same thing here, this is two-sided. It has content to the left of 0, so it's going to be non-causal. And the good news here is what we do have a frequency response. So Fourier transform exists because the rock contained the unit circle. So that tells us what? H of n is absolutely summable, system is stable. So now we're getting warmer. That's a little bit more tractable there. And our final, is this our final choice that we're going to cover? Right, choice 3.
one also?
Yes, it's a two-sided sequence.
Yeah.
And so if it's a two-sided sequence, h of n has content at n equals -1, -2, -3, etc. Since it goes both directions at once. And all you need is it to go, even if there's positive stuff, if there's any negative, it kind of taints the whole thing and non-causal.
Can you transform it into a causal system by
Usually just by delaying things enough. You can typically do that. And so let's go with z greater than 2. And everything outside. Z greater than 2. What does this tell us about the system?
right?
But- Right-sided, exactly. So that's a good start. Right-sided. Luckily, since it's right-sided, I'll write this out a little bit. H of n equals 0 for n less than 0, which is good because, as I've said before, if h of n does not equal 0 for n less than 0, you're in the non-causal regime, but since we're in this case, system is causal. And finally, even though it's causal, it turns out that the region of convergence does not contain the Fourier transform. So we have no frequency response. That does not exist. And system is unstable. So there's all the implications for the Z-transform region of convergences and how that results to something we might more care about, which is impulse responses. So now with all these Ford transforms, we're going to talk about how you go backwards, because in some cases we're going to want to analyze systems or compute outputs of LTI systems using Z-transforms, but you can't do that if you don't know how to go backwards. So our next topic, inverse Z-transform. And so one way to do it, that looks pretty fancy. And if you enjoy the study of complex variables, you might have seen this before. It's a complex contour integral, where this C is a closed contour inside the rock. Inside the region of convergence. And this is a formal method, and from the theory of complex variables, so you've done, I think this is you can evaluate this, I'm trying to remember how, I think it's like a Cauchy integral using residues, so it's ways to do it, but it's kind of distracting, and it's not really what we're going to do here. It's kind of cumbersome and distracting, so we're not going to use this as this is kind of a formal method. We're going to be more engineers and sort of use more rough and ready methods, maybe. Might be a better description. So, less formal. We're going to look at just 3 different ways of doing it. First is very easy inspection. It's clearly a z transform of this sequence, and I can look it up in a table. Easy. Second one, partial fraction expansion. And we'll look at two cases where you can apply that. There are actually more cases, but I think it just kind of gets us off the main topic to go any further than two cases for partial fraction expansion. And finally, one more, power series expansion. This is where you can write out the sequence and inverse Z transform it term by term, or you can use a Taylor expansion and inverse transform it term by term. So whatever sequence expansion method happens to be easiest. So first of all, inspection. And that is, can't get any easier, table 3.1. All you have to do is break up x of z into pieces and inverse transform them. And that kind of brings us to the partial fraction expansion, because how do you necessarily break them up? So let's look a little bit under the hood. You probably used this before in other places. So hopefully this is somewhat of a review. But given if we can write this x of z as a ratio of polynomials in z inverse, which is typically some of the more useful functions. So m degrees at the top, b sub k, z to the minus k. And we'll have an nth degree polynomial in the denominator. A sub k, z to the minus k. So we're going to start with this, and we're going to modify it slightly. So if I multiply the top and bottom by z to the m plus n, so I'll put that up here, z to the m plus n. I'm going to multiply both top and bottom by that. So when I do that, z to the m plus n times the top, what can I do with it? Well, I'm going to do something sneaky. I'm going to take this z to the m and push it through to the each term individually. So I'm left with a z to the n out front, and you'll see why we're doing this in a second. So I end up with z to the m minus k. And so now you can kind of see, all right, k equals 0. I got z to the m. As k goes up, I get m minus 1, 2, 3, all the way to m minus m, which is 0. So you end up with an nth degree polynomial up there. We'll do the same thing down here, use the same trick. So we'll end up with z to the m and push the n through to the other side. And that's n. So now you can kind of see these are going to be an nth degree polynomial and an nth degree. And that's going to kind of set how we attack the problem. So you got 3 cases here. So if n equals m, number of poles, number of zeros. And if n is greater than m, we're going to have, what, n minus m poles, or no, n minus m zeros. That's right. So we'll go through this. N minus m zeros at z equals 0. So if n is greater than m, this is bigger than that, then we can get rid of this and say z to the n minus m, and that's why we have n minus m zeros at z equals 0. We can also go backwards here. If n is less than m, then we'll end up with m minus n poles at z equals 0. And that's clear because if m is greater than n, well, just combine these together and have this z to the minus n. And this goes away, so you have m minus n poles. I think we'll do an example to kind of show how we're thinking about it here. So let's do an example. So let's let n equal 5 and m equal 3. Just plug it through and see what happens. So if we do that, we'll end up with what? Z to the 5th k equals 0 to 3, m is 3, and that's b sub k, z to the 3 minus k, all over z cubed. And z to the what? 5 minus k. So we're just going to plug in some numbers and see what happens. Well, once we have that kind of cumbersome expression written, we can say, okay, z to the 5th divided by z cubed, that's pretty easy. That's z squared. And what am I left with here? Well, this thing didn't change. So that's k equals 0, 3, b sub k, z to the 3 minus k. That term went away. So we're left with this bottom summation. So what's going on? The reason why I wanted to write this out is so you can see that the number, when you write it this way, the number of poles and zeros universally is always the same. So if you look at this, this is degree 3. There's going to be 3 zeros. But there are also 2 zeros at z equals 0. And if you look at the bottom, there's 5 poles because this is a 5th degree polynomial. And so let's put this is the 2 zeros at 0. Then we've got the 3 poles here. Or how about we call them zeros since they're in the numerator. And 5 poles there. And everything adds up. 2 plus 3 is 5. And 5 bottom. So once we have an expression like this, we can also write it, and this is where the partial fraction expansion comes in, is we can also express it, since these are a 5th degree polynomial, basically what it is b0 over a0 times a product of these. So m 1 minus ck z inverse k equals 1 to n. 1 minus, we'll call these the dk's, z inverse. Yes.
What is that symbol?
This is a product symbol, it just means you're going to multiply.
Okay.
So p of k equals 1 to 5 is 1 times 2 times 3 times 4 times 5. If this is pi k, k equals 1 to 5. Hopefully it's barely legible. Let's try that again. Make sure everybody understands the symbol. 1 to 5 of k. 1 times 2 times 3 times 4 times 5. So that's the notation. Instead of a summation, it's a multiplication. So what are we doing here? Well, now we're going to express that polynomial of degree m as these products of these zeros, ck, where the ck's are non-zero zeros, and these dk's are basically non-zero poles. And we're just going to make it a product of them to get whatever degree we need. Now if we look at it like this, the whole formulation for the, I guess, for the partial fraction expansion kind of comes out, and that's what we're going to look at, kind of what's under the hood of that. So we're going to start with, that's what we're thinking about. We're going to divide it into kind of two cases. There are more, but I think two's enough to get the point for what we're trying to do. So what I'm going to call case 1 is the case if m is less than n, and all the poles are first order. So if you have our expression here, and m is less than n, and all the poles are first order, we're going to kind of go through how to extract that expansion. So what we want to do is basically rewrite x of z as a summation from k equals 1 to n d sub k 1 minus d sub k z inverse. Remember, these d sub k's were the non-zero poles. And the point of writing it like this is because this is very easy to z transform. We already know what that is. It's, depending on region of convergence, it's just a geometric series. So that's pretty easy once we have this expression. So for our derivation here to explain how this works, we're going to multiply each side by, just choose some random pole. The ith pole is what we'll do. So if we multiply both sides times this expression, 1 minus d sub I z inverse. So this polynomial expression here, I have to do it for the other side. So we have a sub k 1 minus d sub I z inverse. So we end up with a summation like that. Well, to really see what's going on, you kind of have to expand this and look at the terms. So let's do that. We have ... This expression equals what? Well, if k equals 1, it's a1 times this 1 minus d sub I z inverse all over 1 minus d sub 1, z to the minus 1, plus, and we can continue on, a2, 1 minus d sub I z inverse all over 1 minus d sub 2 z inverse, and so on, ... Well, eventually we will hit this d sub I term, and when we do, what's going to happen? ... a sub I 1 minus d sub I z inverse all over, now k has become I, so we're at 1 minus d sub I z inverse. And so these two terms, you can see, are going to cancel, just leaving a sub I by itself. And as we continue to the end, what do we get? We're finally at n. We'll get a sub n times 1 minus d sub n z inverse all over. Wait, that's a d sub I. Sorry about that. That's the thing that stays constant throughout this whole thing. And now we're down to d sub n z inverse. And so the point of writing all that out is to see that we end up with one of the a sub i's all by its lonesome, which is nice, because the next step, which you've probably seen before, is now we set z to a convenient value, right? So let's let z equal d sub I on both sides of this equation. So we end up with x of z times 1 minus d sub I z inverse over here, and we're going to say that let's z equal d sub I. And then when we do it for all the terms in this expression here, when z equals d sub I, well then it's d sub I over d sub I, which is 1. 1 minus 1 is 0. And so every single one of these terms gets annihilated all the way through, except for this term, a sub I. Right? So we end up with 0 plus 0 dot 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 a sub I plus dot 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 to the end. Everything is 0 because all these terms were annihilated by setting z equal to d sub I. That was the trick that allowed that to happen. Now you might say, well, that's all well and good, but what happened over here? Why didn't setting z equal to d sub I in this expression annihilate this side too? Well, this side doesn't go to 0 because there's a term in x of z, since this is I guess we're multiplying it by both sides. Remember, this is a pole, so there is a part of x of z that has 1 minus d sub I as part of it. And so this annihilates with some part of x of z. And why is that? Because our whole premise was that x of z can be written as a product of polynomials in z over another product. So down here somewhere is a 1 minus d sub I z inverse, which will then cancel with this one so this whole thing doesn't disappear. And so the algorithm that we're going to use, and you probably used it before, is simply keep choosing different values for z and annihilating terms and calculating each a sub I. And we'll do an example to kind of make it more real, but hopefully that sort of shows what's going on under the hood. Now, here's a case 2, which is very similar. And this applies if m is greater than n, and all poles are first order. Looks very much like the other one. If that's the case, we can end up writing x of z as a summation of what r equals 0 to m minus n, m is greater than n, times some coefficients, capital BR, z to the minus r, plus our friendly partial fraction expansion that we just talked about, which are these capital A sub k's for 1 minus d sub k z inverse. And we'll do an example of case 2 with real numbers and everything, so you can kind of see that really case 2 is just an extension of case 1. Now there are other cases where you have multiple order poles, but I think that's kind of tedious and not really all that commonly used. So let's just stick with case 1 and case 2 and first order poles for now. I think in the textbook they show the formula for doing multiple order poles, and it's somewhat involved. So you can dig into that if you'd like. So let's do an example for case 1. So we'll use this x of z and for this there's our x of z, there's our region of convergence. So first off, what's m and n? Well, m was 0, n equals 2. Based on the formulation I used, I kind of stuck with the book's terminology, even though it's a little bit hard to remember because I think numerator, but that's not the case here. N is the degree of the polynomial in the denominator. And the good news, you look at this, well, all poles are first order. So, yep, we're in the right place. This is a case 1 situation. So, let's say, well, we can write x of z as, let's do 1 over 1 minus 1/4 z inverse times 1 minus 1/2 z inverse, which equals a sub 1 plus a sub 2. There's how we have the problem set up. We just want to figure out the a1 and a2. So the first thing to do is choose one of these guys to go first, one of these pole expressions. So if we multiply both sides of this equation by 1 minus 1/4 z inverse, what's going to happen? Well, it's going to cancel one of these. So we'll end up with what? 1 over 1 minus 1/2 z inverse, which equals, multiply 1 minus 1/4 z inverse times this side, that annihilates that one, leaving a1 plus a2 times 1 minus 1/4 z inverse all over 1 minus 1/2 z inverse. We just multiplied both sides times 1 minus 1/4 z inverse. Went through the algebra. Now the next part of the trick is, how do we make the terms we don't like go away? Right? And so let's let z equal 2. Right? So our z inverse equal 2. Right? And if we do that, wait, I'm in the weeds here. What I wanted to do was stick with this. Let's stick with this one first, right? So let's let z inverse equal 4, or z equal 1/4, and plug and chug here. So 1 minus 1/2 z inverse is 4 equals a1 plus what? a2 times 1 minus 1/4 z inverse is 4, 1 minus 1/2, and z inverse is 4. So plugging all the variables in, we've got this. And by design, 1 minus quantity 1/4 times 4 is 1, so 1 minus 1 is 0, eliminating that, which is what we wanted. So we end up with 1 minus 2 equals a1. So a1 is just 1 over 1 minus -1. So there's our first term. And luckily we can just kind of lather, rinse, repeat, as they say. Right? We knocked off one. We can easily do the same to the other. So we'll go back and say, well, I'm going to do it one more time. 1 minus 1/4 z inverse, 1 minus 1/2 z inverse. Plus a2 over 1 minus 1/2 z inverse. So we already got a1, so now we're down to a2, so let's multiply both sides times this quantity. If we do that, we end up with what? 1 minus 1/2 z inverse, which by design will cancel this term. And then we've got a1 times this term, all over 1 minus 1/4 z inverse, plus we multiplied those two times each other, so they cancel. We're left with it, a2 all by itself, which is what we want. So now we let z inverse equal 2, right? And so if we do that, that eliminates this term, this nuisance term, so we're just left with a2, right? So since these cancel, We end up with 1 minus 1/4 times 2. And this is what? A1 times 1 minus C inverse is 2. A half times 2 is just 1. Plus A2. So pretty straightforward. 1 over 1 minus a half. That's just 1 minus a half is a half. So what A2 is just 2. So A2 is just 2. So now we've got all the pieces we need. And we can say x of z is minus 1, which was A1, over 1 minus 1/4 z inverse, plus 2 over 1 minus a half z inverse. And of course, the all-important region of convergence is along for the ride. Nothing changed. Now, one of the ways we can go wrong here is to immediately say, all right, phew, got that done, and you just jump right to the table and inverse z transform the very first z transform you find, and that can cause a problem. So what I'd like to do is to kind of take a step back and say, all right, before we start z transforming this thing term by term and declare victory, let's go back to the original thing and look at it and explain to ourselves what the answer really has to be before you start choosing answers out of the table. So let's take a deep breath and say, all right, first principles here, given this expression, given this region of convergence, what is my answer going to have to look like? And by answer, I mean when you inverse z transform as this, what do those sequences have to look like? Because remember, the region of convergence and the poles and stuff tell you about right-sided, left-sided, and all that jazz, right? So you need to make sure that your sequences are in agreement with that logic. So let's rewrite this x of z multiplied top and bottom by z squared. That's just for the purposes of doing this pole zero plot, so don't forget anything. So if we do that, we've got this. So now, let's pretend we were just given this here and we wanted to figure out what's going on. Well, first of all, we know we have a double zero at z equals 0. That's pretty straightforward. And we've got a pole at z equals 1/4 and a pole at z equals 1/2. So z is greater than 1/2, so we can draw our circle. And say, aha, there's our region of convergence. It's outside that circle. Well, hopefully you remember when you see everything outside the circle, that tells us what? X of n is a right-sided sequence. And of course, if x of n was an h of n, then it would include the unit circle and the frequency response would exist. And as it stands, x of n, the Fourier transform exists. X of n is absolutely summable. But why we really did this is we know x of n is a right-sided sequence. So if you go to table 3.1 and you start looking at the inverse z transforms of these expressions, you don't want to choose anything that's left-sided, right? And that's the purpose of kind of taking a step back. So we go back to table 3.1 in the text. You can see that this is, I think there's an example of 1 over 1 minus a z inverse. So I'll just take down the minus 1. a in this case is 1/4, so that's 1/4 to the n, unit step of n, plus, just bring down the 2, because it's a linear operation. And now instead of 1/1 minus az inverse, you also know this one is right-sided, so you can do this. And so there's your... Now if you go look in table 3.1, I don't have it in front of me, but if I did, I would put it on screen, is that there are left-sided sequences that correspond to 1/1 minus 1/4 z inverse. And I think if you recall, is it like 1/4 to the n, u to the minus n minus 1, something like that? You can get left-sided sequences, but we know that's not the case because we're given the region of convergence is this. So just a note there. Okay, that pretty much squares away case 1. Let's do an example of case 2 that uses what we just did in case 1. So if case 2, let's be given this example, 1 plus 2z inverse plus z to the minus 2 all over this case 1 minus c inverse. So a slightly more complicated example, and z greater than 1. Now if you look at this example, you can see the degree of the numerator and denominator are the same, so m equals n equals 2. So this is a case 2 situation, because what is case 2? Definition. Definition of case 2. I'll just rewrite it here just for remembering. M is greater than or equal to n, and all poles first order. And that's what we have here because none of these are raised to any powers in the bottom. So we've got this. So how do we get those, how do we get this back to something easy to do? So if we go back to this slide, case 2 said the form of x of z was this. Well, we've already gone through the exercise of doing partial fraction expansion and calculating the capital A sub k's. That we know how to do. What about these capital B sub r's? Where do they come from? And that's our present task. So it turns out, as you can imagine, what do we want to do? We want to reduce this an expression in this polynomial so that the numerator degree is less than the denominator degree, so we can go back to case 1. So how do you do that? You're just going to divide them and use long division and end up with a quotient plus a remainder. And that's basically what we're going to do. We're going to say our form of x of z is going to be some b0 z inverse. And we know that it's only one term because these are the same degree as each other. It's the second degree. If you multiply these out, these are also second degree. So let's use long division. And let me see, how do I want to write this? 1/2 z to the minus 2 minus 3/2 z inverse plus 1. And that's dividing into z to the minus 2 plus 2z inverse plus 1. Well, where did I get all this? If we go back to the denominator and multiply this through, that's what we get. So if we were to multiply these guys together in the denominator, 1 times 1 is 1, minus 1/2 z inverse minus another z inverse gives you what? Minus 3/2 z inverse. Multiply this is plus 1/2 z to the minus 2. And so this polynomial over this polynomial. So we're just going to crank through it, this one over this one. So if we multiply this out, 2 times a half is 1, so that's z to the minus 2. 2 times minus 3 halves is what? Minus 3z inverse. And finally that's plus 2. So if we subtract this is what we wanted, because now this second degree goes away. 2 minus a negative 3, 2 minus a negative 3, 5z inverse, 1 minus 2, negative 1. So now we've kind of broken this thing down one level. So now we can rewrite this as x of z equals 2 plus what? 5 z inverse minus 1 all over this polynomial, which I'll just write like this for clarity. But you know that that quantity there is really those two expressions there multiplied together. So that kind of brings us back to our friendly case 1 again, right? We can say, well, that's 2 plus 5z inverse minus 1 all over that product, which is 1 minus 1/2 z inverse. 1 minus z inverse. And the good news is, okay, we understand how to inverse z transform that 2. It's just going to be a 1, right? Because there's no delay, so it's just del of n, just an impulse I meant. And that leaves us with saying, let's focus on just inverse z transforming that using our familiar method. So now we can go back to case 1, back to our normal way of doing this. And just go through your standard standard partial fraction expansion that we've already been doing. So if we quickly kind of do it this time, multiply both sides times this, 1 minus 1/2 z inverse, multiply both sides times that, we end up with what? 1 minus z inverse plus a1 plus I don't care. And I can always let what? Z inverse. Since I multiply it times that, I want z inverse to be 2, right? So let's let z inverse equal 2. So now my don't care term disappears. And so we end up with what? Z inverse is 2 minus 1 for 1 minus 2. Which is what? 9 over negative 1. And so last time through it, multiplying both sides times 1 minus z inverse is what? 5z inverse minus 1, 1 minus z inverse, 1 minus 1/2 z inverse equals what? A1, 1 minus z inverse, 1 minus 1/2 z inverse, plus A2. And to kill all these terms, we'll let z inverse equal 1. So start slashing and burning things, and we end up with what? 5 times 1 minus 1 for 1 minus 1/2 equals A2. So let's see if I can do this arithmetic. 5, that's 4. 1 minus 1/2 is 2. So 4 over 1/2 is 4 times 2, which is 8. So now we can just put it all together. And so we end up with 2 plus, what, minus 9 all over that pole, which is 1 minus 1/2 z inverse. Finally, plus 8 over 1 minus z inverse. And our region of convergence was that. So what does this tell us? It tells us it's a right-sided sequence, so when you start inverse z transforming, don't use left-sided sequences, right? So this is kind of a lookup table problem now at this point. Inverse z transforming that is 2 del n, the impulse, minus 9 times 1/2 to the n, u of n, plus 8 to the 1 to the nth u of n. And that's sort of our final expression. I think this is a pretty good place to stop, and next time we'll finish up the z transform and hopefully move on to sampling at this point.
Professor, I had a quick question.
Yes.
Why do we do the long division?
We do the long division because if you try to go through this using our standard partial fraction expansion, it breaks down if you don't have the numerator less than the denominator. I guess I could do an example of that, or show an example of that next time, or something. But if you go through it, you can get wrong answers from doing the partial fraction expansion technique as I showed it.
I have a question about long division.
Maybe I took the wrong notes, but
Okay, let's see. I might have made a.
this page.
Pretty sure.
It's plus. Oh, it's plus. Wait, it's plus. Can you go back
Should-
to the question?